Good evening, everyone. I'm Maureen Aylward, the Executive Director of TownGreen, and I want to welcome you to this really unique opportunity for us to hear about a project happening through the Woods Hole Oceanographic Institution. It's called the LOC-NESS Project. Tonight we have Adam Subhas with us, and he is the Associate Scientist at Woods Hole. He's going to take it now and do some introductions. But I will say that if you have any questions during the program, please put it right into the chat. We will have a 30-minute Q&A session at the end. So yeah, Adam, so wonderful to have you here and to collaborate on this presentation. Thanks for being here.
Yeah, thank you so much, Maureen, for setting this up and for the opportunity to present to you and TownGreen and everyone here on the call. And I'll just go ahead and share my screen here. Okay, so you should be able to see my presentation now. Excellent. Okay, so like Maureen said, I'm an associate scientist in the marine chemistry and geochemistry department at the Woods Hole Oceanographic Institution. And I'm the lead investigator of this project, the LOC-NESS Project, that stands for locking ocean carbon in the Northeast Shelf and Slope. And we like our acronyms in oceanography, so that we came up with one for this project. And what I'm going to tell you about is this research project that's investigating from a scientific perspective the effectiveness and the environmental impacts of a potential carbon removal technique known as ocean alkalinity enhancement. Now, just a statement about WHOI's position overall when it comes to marine carbon dioxide removal research. WHOI's mission is really to do research and education in the ocean. We really highly value independent research. Improved and extensive ocean observations is a really critical part of that, just understanding the baseline in a changing ocean. Collaboration, you'll see that we're collaborating with all sorts of folks in this project, including town groups like this one to get the word out and educate the public about carbon removal. And we also really focus on ethical and inclusive science. And this statement is linked here in this QR code. Now, like I said, this is a really big collaborative project. So I'm the lead PI, but we have a lot of different scientists working across almost every department at WHOI. So chemistry, biology, physics, engineering. We have marine biology colleagues on the project at Rutgers University. We have colleagues at the Monterey Bay Aquarium Research Institute on the West Coast. We've partnered with a autonomous underwater glider manufacturer, MRV Systems, and we're also collaborating with the Environmental Defense Fund on some of the engagement work that we're doing. Now, to set the scene, we're talking about carbon removal and its utility as a climate mitigation approach. And what this chart shows is how carbon removal fits into this larger question about how to mitigate climate and limit the warming effects that we're seeing right now today. On the x-axis, these are projections, emissions projections out to 2100. So that's, we're starting in about 2000, going out to 2100. And on the vertical axis is carbon emissions in billions of tons of carbon dioxide emitted per year. So, currently we're emitting something like 55 billion tons of carbon every year through the burning of fossil fuels. And that may well continue into the future. But if we want to reach and hit climate goals in terms of limiting warming and other detrimental effects of climate change, there's this internationally recognized target of keeping warming below 2 degrees Celsius or about 4 degrees Fahrenheit. And to do that, emissions overall need to follow this red line. And so we're talking about turning around the emissions from 55 gigatons per year to less than that, relatively quickly. Assume we should have been turning this corner around 2020, and of course we haven't done that yet. And then following this red curve down to net zero. And what this plot really nicely shows is that the majority of how we get there is through a transition away from fossil fuels and reducing CO2 emissions overall. And that's what's shown in this green wedge here. What's clear from this, though, is that the green wedge actually doesn't bring you all the way to net zero and to this 2-degree threshold. So just doing that, we're going to see more than 2 degrees Celsius of warming in the next century. And in order to get to that 2-degree target, this large amount of emissions reductions and a transition away from fossil fuels needs to be supplemented by carbon removal, which is shown as this blue wedge underneath here. And so what this is, negative emissions on the y-axis here, right? And growing from something like less than, from zero up to about 10 billion tons of CO2 getting removed every year and stored somewhere away from the atmosphere where it can't contribute to warming and other effects. Particularly for the ocean, we think a lot about ocean acidification. And this is really a big new way that I think society is starting to think about how to manage carbon and how this approach might fit into climate mitigation scenarios overall. And what's really clear is, this is a really large scale, obviously at the climate scale, and a lot of research needs to be done to evaluate which techniques are viable, which ones might be relevant at the climate scale, and what the associated benefits and trade-offs might be associated with these. So why the ocean? Why are we talking about marine carbon removal in particular? Well, the ocean is the largest reservoir of carbon on the surface of the planet. And this is illustrated by the schematic here that shows the size of the carbon reservoir in these circles. And the size of the circle is the size of the reservoir. So the deep ocean and the upper ocean combined have something like 38,000 billion tons of carbon stored, dissolved in seawater, essentially as bicarbonate or baking soda, just dissolved in water. And the reason the ocean is able to do this, store all this carbon, is because it's alkaline, because it has a relatively high pH of around 8, 8.1 or so. It's more alkaline than fresh water, and this buffering allows it to hold on to so much carbon. And, just to put this in perspective, this is 50 times more carbon than is held in the atmosphere as carbon dioxide. It's 15 to 20 times more carbon than is held in all land plants and soils combined. And it's 5,000 times more carbon than is stored in what we think of as traditional blue carbon ecosystems like seagrasses and mangroves, and et cetera. And I don't want to say that it's not important to think about these really critical ecosystems, forests, rainforests, and seagrasses, mangroves, et cetera, estuaries as really critical parts of the Earth system and really critical targets to maintain in terms of biodiversity, health, et cetera. But in terms of carbon storage and places where we could think about doing large scale carbon removal, a lot of focus is being placed on the ocean because it has so much carbon stored in it already. And the reason it has so much carbon stored again is because it's alkaline, because it is accumulating all of this alkalinity through minerals dissolving, producing calcium and magnesium, and converting all of that carbon dioxide into bicarbonate, into baking soda, baking powder dissolved in water. And so when we think about, the natural system, the way that this used to operate, say pre-industrial times, the ocean had a fairly high buffering capacity, high storage capacity for CO2. And we think of the ocean and the atmosphere as being relatively in balance and maybe just slightly a little bit of CO2 coming out of the ocean into the atmosphere every year. Now, of course, with continued emissions at the scale that I was just showing, there's an accumulation of carbon in the atmosphere, much more than can be taken up by the ocean. We're throwing the system out of balance. And this is not only happening in the atmosphere, but it's also happening in the ocean, not just warming, but also making the ocean waters more acidic. So this is known as ocean acidification. You can kind of think about this like, carbonating a soda, right? You force a bunch of CO2 gas, and a bunch of that dissolves into water. And that's essentially what's happening in the oceans globally. And it's causing a whole other set of stresses on shellfish and other marine organisms. What this also does is it decreases the ocean's ability to take up further CO2 into the future as emissions continue into the future. So the idea behind ocean alkalinity enhancement is that by adding alkaline materials to seawater, which is again, it's part of this natural process of weathering minerals, delivering this alkalinity to seawater, you add buffering capacity, restore the pH of the ocean, and make more room for CO2 all at the same time. And this is a process that happens naturally over tens or hundreds of thousands of years. We can actually see it in geological cycles of ocean chemistry back through time. But the real question is, could this work on the timescale of what's happening with the climate today? And what are the potential risks, benefits, et cetera, associated with thinking about this process at the scale that is needed for climate mitigation? So alkalinity enhancement is not a new approach, actually, in terms of restoring pH balance in natural waters. So ocean liming, or sorry, river liming, lake liming has actually been a relatively common practice all across the US and Canada and the EU and other places to restore the pH associated with acid mine drainage and other things. It's seen real benefits for the salmon fisheries. Here's an example of someone liming a lake to restore pH balance that we got from the Kentucky Department of Fish and Wildlife. So this is a routine practice that happens to balance the pH of natural waters. Now, the other thing to point out is that alkalinity enhancement is also routinely used in aquaculture and shellfish hatcheries. And it's a common way to boost the alkalinity to improve shellfish yields and help shellfish facilities and hatcheries to maintain the pH balance of their systems as well. So it's routinely used in that setting, and it's also routinely used in wastewater and drinking water treatment. So drinking water is balanced actually with sodium hydroxide. Typically, wastewater is often treated with alkalinity as well. It's even popular now to drink alkaline water. So this is one brand that, the pH of this water is 9.5. And my sister is a baker, and I'm typically very food motivated. So I always like to throw in the fact that soft pretzels are actually made by boiling them in a lye solution, and that gives the soft pretzels their characteristic brown shine that we all love on a soft pretzel. So it's routinely used in food production, in water treatment, in treatment of natural waters, and in aquaculture facilities. The question really becomes, what does it look like in the ocean, and could it be used in terms of a climate mitigation approach? Now, we're not the only people asking this question. Uh, there's a large voluntary carbon market that got established in about 2021, 2022 to the tune of $1 billion that has since grown since then. And a number of startup companies have formed to try to answer this need of delivering carbon credits through this carbon market. And these companies are just several of the ones that are proposing and actually actively doing now alkalinity enhancement in the US and in North America. So for instance, Ebb Carbon was just contracted by Microsoft to sequester almost 350,000 tons of carbon via sodium hydroxide addition to seawater, an ocean alkalinity enhancement process in the next 10 years. Captura is operating in LA. They're claiming about 100 tons of year removal. Planetary is operating now in Halifax in the Chesapeake. They're trying to spin something up in Vancouver where they're adding a form of alkalinity known as magnesium hydroxide or brucite. And they actually have seen this process all the way through. So they actually have had carbon credits officially issued to them for this alkalinity enhancement process. And Vesta is a company that's looking at beach nourishment using olivine sand, which is a form of alkaline green sand. And they have a large trial. About 8,000 tons of this sand was added to sediments in North Carolina. I actually think this is a bit shallower than 300 meters. It might be like 25 or 30 feet. Actually, apologies for that. And just to kind of bring this point home, right? This is something that a lot of companies are thinking about actively in terms of their own carbon mitigation portfolios and climate portfolios. So for instance, Microsoft by 2030 is projecting that they're going to be trying to do 10 million tons of carbon removal just for their company to try to meet their own carbon neutrality goals. So this is an ongoing thing, and it's part now of climate projections, both internationally and now at a pretty granular level in terms of what companies are thinking about. Where do we fit in here? We are an independent and interdisciplinary team of 20 plus scientists, engineers, and communicators. We're really committed to a transparent, rigorous, and scientific evaluation of ocean alkalinity enhancement. LOC-NESS is not a company selling CO2 credits and is not participating in this voluntary carbon market. This project is designed to answer key questions about the effectiveness and the environmental impacts of ocean alkalinity enhancement. And this project should not be viewed as a pathway to this climate scale. We're not endorsing climate scale ocean alkalinity enhancement. And although we've chosen to use sodium hydroxide as our alkalinity source to answer these key scientific questions, we're not endorsing its use in other applications of climate scale or industrial scale alkalinity enhancement. So what are the goals of this research? There are companies operating in the water right now, and what we see is a really critical part of a research portfolio is moving into in-water experiments as well. We see this as a really critical part, both to match the scale of what we see happening in the private sector, but also to answer critical unknowns about what this actually looks like in real world settings, and doing that from a transparent and rigorous scientific perspective. So of course, there's evaluating this real world efficacy and durability. This would feed into monitoring, reporting, and verification protocols for the carbon removal, assessing environmental impacts. How do you monitor for those? And how would you regulate those? How would you sort of set limits and safety guidelines around regulations for this new industry? There's an aspect of testing CDR technologies, so identifying potential showstoppers that would prevent something from scaling up, and then potentially to continue to test and scale options that look promising. And finally, this is really important, especially for WHOI, whose mission is partly an educational one, is to educate the public about this work, this research, and this whole field of carbon removal, gather public opinion, build confidence and literacy about talking about these issues, and evaluate how communities view and interact with this research and other activities in this space. Now, again, I said we're not alone in this, so this is actually a federally and internationally recognized research area. The National Academies put out a report on this in 2021. The outgoing administration has a research strategy on marine carbon dioxide removal, and carbon removal is also now recognized part of IPCC level evaluations of the state of the climate and potential mitigation solutions. So we're here, I'm here today to engage with you all, to tell you a little bit about the project, and to have a Q&A after I've finished talking here. A lot of this effort is geared towards educating the public about marine CDR. There's been a lot in social media and other articles about this, and part of doing these presentations is to dispel mis and disinformation that's getting spread about the project. Often people will come in seeing something on social media we have to kind of walk people back and explain exactly what's going on. So part of that is going into that. And then also a big part of these events have been to seek feedback from communities and to incorporate that feedback into the research plan where possible. So what are we doing? We're studying regional data sets. We have a high resolution ocean model of the entire Northeast Shelf and Slope that I'm showing here on the right that we're running as well to really interface between data and the state-of-the-art ocean models. We're conducting biological impact studies in the lab and also taking advantage of WHOI's extensive shipgoing operations to take natural water and do experiments with those natural water samples as well. We're doing a whole series of dispersal and geochemical tests, really honing in on the engineering of this, making sure that it can happen safely and effectively, and pairing that with really near field dispersion and dilution models in a ship wake. We're hosting these kinds of workshops, listening sessions, seminars, et cetera. And we are planning to, we're proposing to do an alkalinity dispersal and continuous monitoring coming up this summer in the Gulf of Maine. And that's one of the reasons why I'm really excited to talk to you because, Gloucester is right there. So we're excited to present this work to you. So who we received feedback from? We proposed 2 EPA permits initially back last summer. Those EPA permits went through a public comment period. We then resubmitted a permit application just for the Gulf of Maine site with some revisions, including a reduced scope of the experiment. I can talk about those details and go into as much Q&A as you want. That new round of application is open for public comment until the end of this week. We have received official consultation and actually consistency on those first applications from Endangered Species Act at NOAA and the U.S. Fish and Wildlife Service, Essential Fish Habitat, and the Massachusetts Coastal Zone Management Office. We've done a whole bunch of community engagement events with all sorts of folks. I think one of the really interesting things about this project is that, as a scientist, I've always wanted my work to be relevant for society and for the climate problem. And I think that is really crystallized with this project. We've talked to so many people and heard so many different perspectives about how people value the climate, the oceans, where people are coming from, trying to incorporate all of these different perspectives, federal, regulatory, legislative, public, fishing, indigenous, all together, and really trying to put that together into developing a research plan that tries to address society's questions about whether this is a viable option or not. We've done a whole series of interviews with all sorts of media outlets, and we've also done surveys, targeting feedback specifically from commercial, recreational, et cetera, fishermen, lobstermen on species of concern and the location of the trial. What do we hear about typically when we do these events? The biggest thing that we hear about is the commercialization and the scale of these proposed climate solutions. This is as proposed, a very rapid scaling of something that is just a completely new way of thinking about carbon and carbon management. And that's there's a lot of uncertainty there. There's a lot of hesitancy. There's a lot of skepticism. And, we're right there with you. That's one of the reasons why we think this research is so important to do. We're doing this research so that some of these questions can get answered. People are concerned about ecosystem impacts. So things about impacts on plankton, commercial fish larvae, impacts on higher trophic levels like marine mammals and turtles. And then there's just the spatial concern of overlap with existing fishing activity in the region as well. That's also been something that we've heard a lot, and we've also tried to incorporate in terms of the scope of the project. So again, how have we responded to this? We've really increased and expanded our outreach activities, including events like this. We've begun higher trophic level experiments. We've done a lot of experiments on phytoplankton, and there's actually a whole series of 19 scientific papers that just came out on the effects of alkalinity enhancement on phytoplankton and zooplankton and copepods from international researchers. We've begun those experiments ourselves to try to sort of emulate some of those and really tailor those experiments to these specific experimental conditions and hopefully feed into the regulatory framework. We're working with the EPA, so we see a lot of this as feeding directly into how regulations might go into place. We've done a lot of deep dives into the biological and fishing activity data sets in the region. One of the advantages of doing this research here in the Northeast is there's so much data on all sorts of aspects of the marine ecosystem and the chemistry and the physics and everything. And so it's been a really rich data set to dig into. And we've also considered a whole suite of alternate dispersal locations. So you may have heard we were proposing one experiment south of Martha's Vineyard. We have since moved now to focus just on the Wilkinson Basin area, the Gulf of Maine. We also considered a number of other sites that were proposed that because of our criteria, we had to no longer pursue. So where are we ending up with this experiment? It's in the Wilkinson Basin area, the Gulf of Maine. The proposed project would happen at this pink circle here, and that's actually to scale. We're proposing to do this in the summer of 2025. The patch size of what we would do, we would disperse alkalinity in this patch, and that patch size would have a slightly elevated pH of a few tenths of a unit above the sort of background pH. And that whole process, I'll just skip to the next slide here, would take, we're anticipating it taking about 4 hours to do that dispersal. During that time, we would probably set up some kind of just, Coast Guard perimeter just to make sure that we can operate safely. And then the idea is that we would move into a monitoring phase where we are constantly monitoring the chemistry, the biology, both from measurements on a ship, but also measurements that we can actually take from space with satellites, with autonomous vehicles, continuously 24 hours a day for an entire 7 days straight. And what this white circle is the sort of extent of where that monitoring period might end up. So it's not that the patch will spread out to fill that entire circle, but it'll start to spread and dilute and disperse. And of course, as it does that, the pH will continually lower back to baseline. It'll be some small circle in here, and then it'll start moving with the currents and tides and getting pulled and drawn and dispersing as it goes. And so what this white circle is based on our ocean model runs and our knowledge of the currents and tides in the area. This is sort of the extent of where you might anticipate seeing our monitoring vessel over this 7-day monitoring period. And again, there would be no restriction on vessel activity in this white circle over that time period. The permitting that we're going through is through the MPRSA branch of EPA. This is relevant for all waters sort of past the baseline and out of the coastal zone. So it's a federal permit, and it's a one-time permit. So we're permitted. We're submitting a permit for this one research project, and after that, we're done. We do think that we can answer a lot of these unknown scientific questions about the effectiveness and the environmental impacts with this one study. We're really interested in continuing the conversation. And of course, happy to come back and present as we get some more information and data on what we've been finding. I think what I'm going to do is stop there. Happy to take questions, open it up for conversation, and maybe I'll stop sharing my slides. I have lots of backup slides that I'm happy to share if we want to get technical. As a scientist, I'm always happy to get technical, but I'm also happy to answer sort of whatever questions and comments the audience has. So I'll stop there. Let me stop my share, and we can open it up for Q&A.
Great. Thanks so much, Adam. That was really interesting. That was a great presentation. Well, I'm wondering if you've answered some of the questions I sent to you that came to us early, but One of the questions just to kick it off is if the Ocean Alkalinity Project moves forward to full-scale carbon sequestration, how many tons of carbon could be removed from the atmosphere, and what are estimated costs per ton for sequestration?
Yeah, it gets at the scale. We we always get asked questions about scale. I think it's so important just because, this is a potential climate solution, right? So it's really important for us to be asking questions about the scaling. Um, so there have been a number of modeling studies using, pretty sophisticated ocean models and a whole other set of constraints that place the potential for ocean alkalinity enhancement in particular to be operating at the sort of, at the billion ton per year level with, you know, in terms of the models, relatively small increases in alkalinity. So we're not talking about huge swings in ocean chemistry to accomplish this. Um, so there is the potential there. I think the cost is a really interesting question. There's this kind of benchmark of about $100 per ton that people often cite. Um, a lot of the alkalinity enhancement approaches are hovering around that, I would say, like order of magnitude, hundreds of dollars. And I think a lot of that comes into life cycle assessments, in terms of the actual effort and the net carbon removed. If you think about, from soup to nuts, right, cradle to grave, how much carbon did you emit? How much carbon did you remove? What is the actual cost? That it's sort of like in ballpark hundreds of dollars per ton right now, and it could drop right as this scales. Um, and then I think the other interesting question, right, that I think we're really focused on here too is, is there a cost to marine ecosystems, right? What is the cost in terms of biodiversity and ocean health? And I think that's a really critical question that we're hoping to start getting answers to with this project in a transparent way, right? That is not associated with the carbon market that has this interest in selling carbon credits. Um, and that's a really critical part of just the societal conversation around how this might get scaled up.
Do you have any ideas right now about what you're looking for in terms of impacts to biodiversity in the marine?
Yeah, so one of the we have this really interesting study that I'm like really excited to get out in the literature that we've looked at sort of baseline data in the region, everything from chlorophyll all the way up through marine mammals and right whales, et cetera. And focusing on understanding what's driving biodiversity and ecosystem richness in the region. And then starting to think about how that might overlap with these ocean activities. I think one of the things that's come out of these early studies, specifically on the base of the food chain, like phytoplankton, is that a lot of these organisms are incredibly resilient to changes in alkalinity and pH. And in some cases, even, there's some evidence of a little bit of a mild negative response, but even some evidence of a benefit, right? I mean, organisms are feeling the effects and the stresses of ocean acidification. And this is one way to try to alleviate some of that stress. So it's a complex question, no doubt, and it's going to require a lot more research than what we're able to do here. But we're hoping to get a good start on that process through this project.
That's great. A couple more questions. Why Wilson Basin?
Yeah, so okay, I'm going to share a slide on this because I do think it's useful to just kind of go through our various criteria for this. Um, okay, so what are we looking for in terms of an experimental site? One is stratified waters. So the idea is that in the summertime in particular, the water is heavily stratified. So you think about when you go in the ocean, right? Right on the edge, it's warm, and then your legs go under, and you hit that cold layer, right? And what is really critical for this is that there is that stratified layer that holds this alkalinity at the surface, which allows it to interact with the atmosphere and actually take up CO2. That's a really critical feature, and that's moved us towards the summertime when you have this really high levels of stratification. We're looking for slow or constrained currents to minimize travel time and the loss of the signal through dispersion and dilution. And the Wilkinson Basin, specifically at this location, it's kind of like a giant eddy. And so it really does sort of hold the water at that one place, which makes the monitoring a lot more straightforward. There's also in this region in general relatively low alkalinity compared to the open ocean. And that's really because of all the river input, all the freshwater input from the coast. What that means is that Northeast waters are actually more sensitive to ocean acidification to begin with. But what it also means is that you get more bang for your buck in terms of adding alkalinity and actually seeing that signal in the CO2 uptake. So from that perspective, this region is actually quite a good area to study from a chemical perspective. The other thing is that we've really focused on looking for areas of the entire Northeast Shelf, and we really have extended our search for a site all the way up and down from the Mid-Atlantic Bight all the way up to Nova Scotia, looking for places with lower biological activity to minimize environmental impact, and looking for places where we have minimal overlap with ongoing ocean uses, such as fishing and offshore wind. And I can walk you through all the reasons, we have lots of data on all of these, but essentially the Wilkinson Basin satisfies all of these criteria for us. And that's kind of why we've ended up there.
Great, thanks for that. A couple of questions from the chat. If ocean was previously more alkaline, would this test or scaled up addition recreate the prior alkalinity of the test areas or larger areas?
Yeah, that's a really interesting question. Pre-industrially, obviously the ocean was more basic, and we can actually measure the decrease in ocean pH, the increase in acidity. The oceans become about 30% more acidic. And part of this could alleviate that acidification back to pre-industrial levels, and it could also help the ocean take up more carbon while sort of not provoking that additional acidification. And I'll also say, I think this is an interesting question just from this longer term perspective, right? Is that this alkalinity enhancement is actually the way in which the ocean will naturally deal with all of this extra carbon dioxide. And the way it's going to do that, right, is by, you know, coral reefs are going to start, stopping to calcify. Deep ocean sediments, so, shells of organisms that have already died are going to start dissolving away. And we actually see evidence of this in the geological record when there were big volcanic events, other, big sources of CO2, you actually see the disappearance of calcium carbonate shells in the geological record. And so, the question becomes if that's going to happen, if that's the result of all of this of all of this CO2 emission, can we avoid that effect and try to do this in a way that is safe and effective on the timescales that we're talking about in terms of being relevant for the climate?
Thank you for that. Another question from the chat, and then I'm going to open it up for people to ask live. How quickly is carbon taken up by the ocean water? If OAE is safe and effective, can it be scaled up? Is there a limit to the amount of carbon that can be captured by the ocean?
Yeah, these are all great questions and questions that we've asked. So carbon is actually taken up fairly slowly relative to something like oxygen. Um, One of the advantages of a test site, a study site in the Northeast Shelf, on the Northeast Shelf, and specifically the Wilkinson Basin, is that uptake timescale is actually quite a bit faster. So it happens on the timescale of sort of 10 to 14 days. We're going to be out there monitoring for a period of 7 days. And so we're actually hoping to capture with direct measurements the actual carbon uptake into seawater. And we think that this site is actually uniquely situated for us to be able to do that. Um, and just to give you, example, globally, the oceans are taking up something like a quarter to a third of all CO2 emissions every year. So out of that 55 gigatons of CO2, that would be something like 10 to 20 gigatons, billions of tons of CO2 that the ocean is taking up every year at the cost of ocean acidification, right? And in terms of the limit, the storage capacity is immense. There, it seems like the oceans can accommodate, especially in terms of this alkalinity enhancement approach, a really large amount of carbon storage. And we actually see evidence for this again in the geological record. So glacial interglacial changes in carbon and alkalinity in the ocean are sort of on par with the amount of alkalinity addition that would be needed for this climate mitigation approach. So it's not impossible that this could happen and happen at scale, but I think the real question is yeah, whether it can happen this quickly, right? And if that can happen safely. And I'm just seeing is there a limit to the amount of cost-effective alkaline material? Yeah, and this is something, there are all different sources of alkaline material out there. This gets into this life cycle analysis that I was sort of, hinting at earlier. Um, a total open question. Some people are working on this. We're actually partnering with a Swiss group that is looking at a life cycle analysis for some of these approaches and trying to feed our data into those economic evaluations to try to see, yeah, is this cost effective and can actually remove CO2 in the net sense and be a benefit for the climate.
Great, thanks, Adam. Would anyone like to ask a question? Any of the participants? You can raise your hand, or you can also just, I think Tom can unmute you. Anybody? Okay. Adam, I'm wondering if you might address maybe some other kind of classic questions that you're getting
Hmm.
from folks. Is there anything that you've heard in different audiences that might be helpful for our participants to hear from in terms of questions and an answer?
Yeah, I think some of these, we get these questions, and I really appreciate, the sort of scale questions. We get a lot of those. We also get questions about the impacts on phytoplankton on larvae. So in the fishing community, we often get asked about, the sensitive life stages that in like specifically live at the surface of the ocean or hanging out in the surface of the ocean. We've actually started to do those experiments, and the first set of experiments that we're doing is actually on Calanus finmarchicus, which is a copepod. It's a critical food web species. It's the main food source for right whales, for lobster larvae, et cetera. And so we've really seen that as sort of the high priority target, but we're hoping to move into some experiments on other organisms like uh, commercial fish larvae, lobster larvae, even. So we're pairing with partnering with the Northeast Fisheries Science Center for that work. Um, and really trying to evaluate, can we look at exposure time, exposure limits, and try to get those experiments to be relevant for what's happening in the ocean and also relevant for regulators who are thinking about like how to go about regulating this in terms of setting safe operating limits and things like that.
Thanks, Adam. We do have a question from Clay. Go ahead and ask your question.
Hey, so I was curious, where like the source of the sodium hydroxide is going to be coming from. I think most of it comes from petroleum production, if I'm not wrong. Is that correct? Or
Um, yeah, so the sodium hydroxide that we're using comes from, it's essentially you essentially like hydrolyze water or like a brine solution, and you split it into sodium hydroxide and then hydrochloric acid. I'm trying to remember the name of the process. I can't name it off the top of my head. Sometimes you also sort of take it all the way to forming chlorine gas on the other side. This is a big part of the potential economic scaling of this approach because you're basically producing the same amount of acid as you are base, and then you have to figure out what to do with that acid. That's a huge like life cycle assessment. Like, could this actually scale question for using sodium hydroxide specifically? For us, we've found it the best material for our experiments because it's a liquid, it rapidly dissolves in water, and it quickly disperses. And what that means is we can really hone the experiment on understanding once that alkalinity is dissolved in water, how fast does the carbon get taken up? How does it get dispersed? And how are organisms interacting with this elevated alkalinity patch? Other approaches like magnesium hydroxide, you would add as like a slurry. So it'd be like a mineral kind of solid liquid mixture that you can source from, you can make it industrially or you can source it from geological sources. Limestone is another one, right, that has essentially like infinite amounts of limestone around. And then it becomes a question of what's the energy associated with mining or producing these materials? Can you get enough of it? Can you grind it fine enough? What are the issues with other trace metal contaminants like chromium or nickel that might come along with those sources? There's all sorts of other issues with those materials. That's another reason why we decided to try to keep this relatively simple experimentally and focus on sodium hydroxide for this scientific experiment. But all of these options are kind of on the table for ocean alkalinity enhancement writ large, and they're all kind of being explored by these different companies right now.
Thanks, Adam.
Oh yeah, chlor-alkali is the process, and a lot of it is used in the petroleum industry. I don't know if it's specific for that. I don't know how much is going to that versus other processes, but like I said, it's really routinely used in all sorts of industrial applications, including drinking water and wastewater treatment.
One more question, Adam, and also if you, Clay, do you have a follow-up question? Tom, can you unmute him? Yeah.
There
Go
you
ahead.
go. Sorry, I can't unmute myself for some reason. Um, does the fact that sodium hydroxide mixed into water is an exothermic reaction, does the temperature that it creates, the increased temperature, is that something you guys will be measuring, or do you think it's just such a small amount in the grand scheme of things that it wouldn't do anything?
It's a really good question. That came up in the first round of public comments. Someone mentioned this, and we were like, "Oh, do we have to think about this?" And we've done a number of flume tests, actually, like large scale flume tests, and we don't see any evidence. The dilution ratios are so high. We're diluting to ratios of greater than 10,000 to 1 in seconds. It's incredibly rapid, and so we aren't expecting to see any sort of temperature increase associated with that level of dilution, but we are going to be measuring temperature sort of continuously in real time. So we should be able to see if there is a temperature effect with our data.
Cool. That's kind of what I figured. My daughter has a really quick question that may or may not be applicable. Go ahead.
How much salt is in the ocean?
How much salt is in the ocean? That's a really good question. So let's see. There's about 35 grams of salt in every liter of seawater.
I mean, a liter is like this much.
Yeah, it's like a Nalgene bottle, so in a big Coke bottle, there would be 70 grams of salt. And then I'm trying to remember how big
So much salt
the ocean is in terms of the number of liters. This is a number that I used to know off the top of my head, and I can't do it. But there's a lot of salt in the ocean. Yeah.
So much salt. Thank you.
Yep.
There's a question about timeline, and you may have mentioned this earlier during the presentation, but I just, could you give a sense of what the timeline is for this? I know you mentioned the summertime, and just repeat, when do you think you're going to get started? And is there anything that you need before you get started?
Right. Yeah. So just as we did do water tracer experiment. So just using this fluorescent water tracer dye. It's essentially like food coloring. It's completely non-toxic. And one of the advantages of that is that we can track just the dispersion of the water, like where it goes without any alkalinity at all. And we can detect it once you can't see it visually anymore, we can detect it with fluorometers and really sensitive instrumentation. And the cool thing about that is you can also see it from space with satellites. So we're planning on using satellites to do some of this monitoring too. We did an experiment just with the dye alone in 2023, and that has guided a lot of our monitoring strategy and the revised permit plans that we've submitted now to the EPA. Public comment period for this new permit application closes at the end of the week, like I said.
Mhm.
We're going to sort of, go into sort of consultations with the EPA around their final determination. If that all goes according, if they end up issuing the permit, we have everything pretty much lined up to be doing the experiment this summer, late summer, probably sometime in August is the idea. And again, it would be, offshore in the Wilkinson Basin area of the Gulf of Maine. And so that is the plan. We would then have a series of reports that would be required by the EPA. So I think a 3-month preliminary report, a 6-month report, and then a year out. And of course, we'll be continuing to do informal updates with anyone who wants to hear about how everything went. So, happy to stay in touch and continue to collaborate on getting the word out about what we
Oh, yeah,
find.
absolutely. If you have an update, we'd love to host you again. There's another couple questions in the chat that I just pull forward. If limit of freshwater rivers in the EU and the US for decades, how is this data relevant to use in the ocean? Guess. Can you see that?
Oh, I see. If lime, I think he probably means if liming of freshwater in rivers
Okay, okay.
used. Yeah. So I think it's relevant in that liming has been done and it has been done successfully in natural waters with potential real co-benefits to lake and river ecosystems. But I do think that, the ocean is unique, right? And it's an open question how relevant that research is. And that's one of the reasons why we think that doing this research in the ocean is so important to start answering some of those questions for the marine environment, because there are unique things about the oceans that you're just not going to capture with those freshwater studies.
And related, there's another question from Tom about, does the process need deep water or could it be done in the Great Lakes?
Yeah, so I think it's not so much deep water because it really does require the alkalinity to stay at the surface and interact with the atmosphere. But the question is like, what would the capacity be if you were to do alkalinity enhancement in the Great Lakes? What would the total storage capacity be in the whole lake system to take up CO2 and store it? That's an open question. I know some people are thinking about this. So there is a company called Carbon Run that's operating doing river liming in Canada as a carbon sequestration and removal approach. And so, people are trying it. I actually have a project looking at just the natural alkalinity cycle in the Mississippi River, which is, at the 12th largest river by discharge in the world, huge plume in the Gulf of Mexico, just trying to understand some of these natural processes and how they might interact with the marine system and at that interface. Um, and yeah, it's a total open question whether freshwater bodies could work. I think the other question is there's a lot of demands on freshwater globally, right? And is this the best use of freshwater, or could it be used for other purposes? I think that's another sort of societal question.
There's so many things to think about with your presentation, Adam, and I don't know, as we come up to the 7 o'clock hour and need to close, are there any sort of some final comments or opportunities maybe to provide public comment if people wanted to?
Yeah, I'm just gonna pull this up. This slide is a little out of date because it has this presentation as an upcoming presentation, but let me just share my screen here. So this we are doing, just did this Gloucester event. We're going to do another webinar associated with the Elastic Coastal Acidification Network in a couple of weeks. But this QR code, if you scan it, does go to the public comment website. And, you know, feel free to send in a comment, post your thoughts. Again, it's open until 11:59 p.m. on the 14th. So, yeah.
Great. We could just leave that up as we say goodbye. Adam Subhas from the Woods Hole Oceanographic Institution, thank you so much for joining us this evening. And TownGreen has been thrilled to host you for this informative webinar. And we would love to bring you back when you've got some more details. We'll be here. We'd love to host you again. So thank you to everyone who was on the call tonight. We are recording this, and so we'll have something out to you at some point in the next week or so. So thanks, everybody, and have a good night.
Thanks, everyone. Thank you, Maureen.